Now we're going to take a look at equations that use trigonometry. Let's look at this equation and say that I want to solve it from the interval of 0 to 360 degrees. The idea works the same as when you're in algebra. You want to isolate the angle itself. So I'm going to add square root of 3 to both sides, and then I'm going to divide by 3 so that I get tangent theta equals the square root of 3 over 3. Tangent theta is positive, so it's in quadrants 1 and quadrant 3. The reference angle is 30 degrees, so I'm asking myself for what angle is tangent equal to square root of 3 over 3. That's in my trig chart, which is the first place you should go before you touch a calculator. Now, I know that it's 30, so I'm going to find all solutions. I need to find the quadrant 3 angle. So if you remember when we learned about reference angles, if I want to find the quadrant 3, I was subtracting 180 to get back to quadrant 1. We apply that in reverse, so I'm going to add 180 to get to quadrant 3, so that I have two answers. I have 30 and 210 degrees. If I wanted an infinite solution set, I could say I could add any multiple of 180n, and that would give me every single solution with no restriction in the domain. Now this one is a little bit tricky, right? Because I have multiple trig functions in play here. So what I'm going to do first is I'm going to get all of my trig functions moved over to the left. Then I'm going to look at this and say, well, I have multiple variables involved, and I have common factors. So I'm going to factor cosine theta out. Then I'm going to set each piece equal to 0, just like when you learned about quadratics. I know that cotangent plus 1, if I'm solving for theta, I'm going to subtract 1 from both sides. And then I'm going to say for what angle is cotangent equal to -1 in quadrants 2 and 4. And the quadrant 2 answer that I would have is 135. To move from quadrant 2 to 4, you would add 180 degrees, and that's where 315 comes from. We know that cosine is equal to 0 on the axis, on the y-axis, which is 90 degrees and 270 degrees. So then I have a solution set with 4 answers. This one is actually in quadratic form. So we can solve trig functions that are in quadratic form, but what I want you to look at this as, think about this as 3x squared minus x minus 2. If we think about it that way, we can factor this to 3x plus 2 and x minus 1. So we're just sort of ignoring the fact that it says sine for the moment being. Then I set each equation equal to 0 and I solve for the sine. So I'm going to have minus 2, then divide by 3 for the top equation to get -2/3. Then for sine x minus 1, I'm going to add 1 to both sides to get +1. Now, -2/3 is not found anywhere in my trig chart, so this is going to be an issue. They also want the answer in radians, so I need to convert my calculator over to radian mode, then type in sine x equals -2/3 or sine inverse of 2/3 so that it finds what that value actually is. Once we get that value, we know that it has to be negative in quadrant 3 and 4. So with that, we're going to use the reference angle to be able to move it from quadrant 3 to quadrant 4. And that's the process with x being plus pi and 2 pi minus that angle. And then for sine of x equals +1, that only occurs in one place, and that would be at pi over 2 because it's going to be on that axis. And my solution set is not very pretty, and that's okay. Now, what about this one? In this situation, I have that 1 over on the other side. So I'm actually going to have to distribute cosine first, and then bring the 1 over so that I can work on solving it. Now, this is a quadratic, just like if I had x squared plus 2x minus 1. I cannot factor that. So I am going to have to use the quadratic formula and sort of ignore that cosine for now. When I do the quadratic formula, this is my answer. Then I'm going to take my calculator and I'm going to type that in because that answer is not found in my trig chart. And I'm going to use my reference angles to find the other solution in quadrant 4. So in quadrant 4, we would be able to do 360 minus the quadrant 1 angle, and that gives us the quadrant 4 angle. And then when I'm looking at the plus or minus of the quadratic formula, so going back to here, if I have -1 minus square root of 2, that becomes entirely too large for the domain of cosine. So there's no solution for that part of the quadratic formula. Now, what about this one? I still have multiple trig functions involved here. So what I would do is, if I square both sides, I'm going to be able to FOIL the left and set it equal to the right. I know that cosecant squared equals 1 plus cotangent squared. So I'm going to replace that so that I have the same trig function all the way across. Then I'm going to simplify, and the cotangent squareds are going to cancel out. I'm going to isolate cotangent, and I'm going to find where in the trig chart does cotangent equal square root of 3 over 3. And that would be at pi over 3, and the reference angle 4/3 pi. 4 pi over 3. And just like we did with the root radicals, we have to check for extraneous solutions. So we're just going to go ahead and check it in there. And we see that the left side, I get -2 square root of 3 over 3, which is not equal to the positive side. So there is one extraneous solution, and that's for pi over 3. Now, what about this one? Solve for 2 cosine x over 2 minus square root of 2. I don't have other trig functions involved here, so I can go ahead and isolate cosine. But I have cosine of x over 2. That is a half angle identity. So what I would do here is I would say, for what angle is cosine square root of 2 over 2? Well, that's at 45 degrees. So what happens here is I need to take that 45 degrees and account for, I have x over 2 equals 45. So to solve x over 2 equals 45, I would multiply both sides by 2, which would give me 90. So if I had pi over 4 times 2, that would be pi over 2. If I had 7 pi over 4 times 2, that would be 7 pi over 2. However, 7 pi over 2 is not in my domain that they gave me from 0 to 2 pi. So I only have one answer in my solution set. If you wanted to graph it, you would be able to graph it and solve for the intercept, but you would not get those nice pi answers in there. Now let's look at, where is the cosine of 2x equal to sine x? Well, I'm going to use my double angle identity to relate cosine to sine so that I have the same function. Then I'm going to factor it and set each parentheses equal to 0 and solve for the trig function. Now I'm going to use the inverse process to solve for my angles, and there's my solution set. A lot of factoring, guys. You've really got to be strong with your quadratics. Next, let's look at this one. This one, I have 2 different trig functions again, so I have to somehow get the same trig function. If we look at 2 and we factor it out, we get cosine squared theta minus sine squared theta, which equals cosine of 2 theta. So I get cosine of 2 theta equals -1/2 once I solve that double angle down. Since cosine is negative in quadrants 2 and 4, the solutions would be here. Then I have to account for, well, it was 2 theta, so 2 theta equals 120, means I need to divide both sides by 2. So we're not accounting for the value in front of the theta until the very end. Now I have a graph that I'm looking at, and I'm told some information about this graph. I'm given, it's a sinusoidal curve, so it's repeating, and I'm talking about its frequency. If I wanted to find the frequency of the pure tone shown in the graph, that's how many cycles it's going through. So if I look at this graph, it goes through 4 cycles before the x value hits 0.0182. So that means there are 4 cycles. So we're not actually doing an inverse function here. We're looking at this actual value. Now, that means if it's 4 per 0.0182, if I want to find out how many cycles per second that is, then I would be able to convert that over to 220 cycles per second. And just as a review, the time that it takes to complete a full cycle is going to be called our period of our graph. So this is reviewing the information that we've already learned, but applying what we have to it.